what we have been doing is gathering some evidence for some dual descriptions of large N gauge theories in terms of string theories. In particular, we started getting some intuition about the fact that there ought to be some dual description just by considering large N gauge theories and seeing how diagrams organize and seeing that the kind of cartoons that we use to define what string theory is as a sum over surfaces is nothing but what we get when we take the large N limit on any theory that has a large number of colors, matrix model, gauge theory, whatever. So there ought to be some duality between a string theory and a gauge theory. And even just by these very hand-wavy arguments, we can immediately see that single trace operators, if you consider correlation function of a bunch of them, this looks exactly like a scattering of n single strings. So there should be some map between single trace operators, trace of some field to some given power, and a single closed string state. We see that the parameter G string that tells you the power, that tells you how much it costs to split string is related to G and μ squared, okay, to whatever the coupling of your gauge theory is. It is, this one is the most obvious one, to the extent that I never wrote even G and μ squared when we were doing matrix model. I wrote immediately G string in the place where you would normally put G and μ squared. We saw that there is a notion of large N factorization, which just means that leading order strings want to propagate freely and then they start interacting. So this matches again our intuition. And this also tells us that not any theory will have some neat description in terms of a string theory if you don't have this kind of large N factorization. So this large N is important. And the map between the 't Hooft coupling we said should be somehow related to the string tension. Because for a given topology, we sum over all the graphs, which is the same as summing over all the fluctuations. But by this kind of argument, you cannot find out what is the precise relation. So there I did not write an equal sign or even an arrow. I just said it should be related to the string tension. Okay. Then we have another picture that will tell us that something like this should happen, coming from this idea of open-closed duality, that you can think of a brain both as a place where open strings end, or as an object that emits gravitons and therefore deforms spacetimes. Good. And this point of view, again, tells you that you should have some large N picture, because you want to have a big stack of many brains so that you can think of it as some heavy object that deforms the spacetime, but which is different from the probe, some heavy object. So again, it hints that you should have some large N limit. If you have an object with n brains, naturally you get a gauge theory with n colors, because then your massless fields will have two indices ij, so then you are led to gauge theory, so it all supports the previous interpretations. And then you went on and said, okay, let's try to take a concrete example. For example, let's say we have three-dimensional brains for concreteness, and we put some D3 brains. And we went and asked, okay, who are the low energy dynamics of a D3 brain? Well, a D3 brain, if we imagine it's there at the blackboard, it's described by some n equals 4 super Young Mills. It's the theory that lives on the brain, plus gravity outside that decouples from it. So this is what it is. And let me emphasize that once you say that you have a physical description of two systems that they decouple, of course this is not an observer-dependent statement. Either things decouple or they don't. Okay? And we argue that they did, so we have these two decoupled systems. On the other hand, we ask, what is the geometry if you have some heavy hyperplane, which is what these brains are? What kind of background does it deform? And okay, I did not tell you, I did not show you, but I told you that what they do is they deform some spacetime, they create some spacetime, and we saw that when we zoom close to the brains, we got AdS 5 times S5 spacetime. And we saw that any excitation, anything that goes on close to AdS 5 times S5, from the point of view of an observer at infinity, which is focused on low energies, it looks like some low energy process. There's also low energy gravity, and I told you that by the usual reasons that gravity decouples, but also because AdS can be thought of as a box, the two systems also decouple. Okay? In other words, even if I am close to the brains and I'm in AdS, what happens is that I know that outside, I mean very, very far away from the brains, there will be gravity. But AdS works as a box. So for me, I'm kind of protected from what is outside. Okay? So if I'm here close to the brain in AdS and I start throwing particles, they come back and so on, I live in my own world, my own box, and then very far away there would be gravity, which would be decoupled. Okay, and if we follow the parameters, and I tried to follow them more or less carefully yesterday, we see that as we expect, G and mu squares is G string. Okay, that works very well. And furthermore, we establish a precise dictionary between the tension of the string, or rather the length, the radius of AdS spacetime in units of string length, and the coupling. So the coupling is indeed related to the tension. And I remind you that what appears multiplying the string action, so the action for the string, will be given by the tension, square root lambda over 2 pi, and then some integral of G mu nu of x, dx mu dx nu, where this stuff is dimensionless. In other words, for example, here you can explicitly see that the metric, it has some L square overall that you factor out. You absorb it together with alpha prime. You use the definition of what L was in terms of the number of branes and so on, and you see that what you get is exactly what we were calling Tuft coupling outside. Okay? So this metric here, for example, is what you get if you use these variables here. Okay. Let's see. Okay. Good. So now, today let's try to provide some further evidence for what we have seen so far, some further evidence for why this kind of picture that we are building makes sense and why it is more or less inevitable and why some features of this duality that at first might seem very surprising, they better be as they are. For example, as I said in the very end of the last lecture, it's kind of surprising that we have a duality between a gauge theory in some dimensions and a theory of quantum gravity, which should be something much more complicated in higher dimensions. Okay, very good. But before, let me just emphasize something basic, something important about this geometry. So this geometry, remember that I said that you can go to this coordinate z, where this becomes, it looks like you have some Minkowski space, and then you have several foliations of Minkowski parameterized by this z, so you have like various copies of Minkowski. As z is increasing, this Minkowski is becoming smaller and smaller. And you have z equal to 0, which is what was before r equal to infinity, which was going far away from the brain, trying to go far away. Okay? So this z equal to 0 is the boundary of AdS. Z equals 0 is the boundary of AdS. And z equal infinity, which is the interior, or r equal to 0, this is where the branes were originally. Okay, this confuses some people because some people get confused by this. Because what happens is, you see the boundary of AdS is not where the branes were. Okay? So we are saying that at the boundary of AdS we have a CFT, but actually the branes are not at the boundary. The branes were originally there. Yeah, but this is total, it makes total sense. When you have, say, the proton, the example of the proton, and we have some heavy proton, which is at r equals 0, and then you have some probes that scatter by. Right? Now you want to ignore the proton and replace it by a non-trivial background. But where should you put your probes if you want to insert them? Of course you should put them at infinity. You are not going to put the probes exactly at r equals 0. So we replace the existence of the proton by the full background, and we can say that probes, as before, should still be sent from infinity. They are not sent from where the probe was. So similarly, from the brain, what we do is we send some probes from far away from the brain for the region where they start feeling the brain, and that's where we scatter stuff. Okay? And the brain is the full background that the brain is generating, is what the space-time is. Okay? So boundary of AdS, you can imagine it as the region when we are entering this near horizon geometry, so it's the region where we should put the probes. Okay? Okay, very good. So what I want to say is that I don't like very much saying that the branes are here or there. You just replace the branes and trade the branes by some background that lives everywhere. Okay. I mean, it's a bit, okay, it's true that the proton was at r equals 0, but I mean, physically that's a bit irrelevant. What matters is that the effect of the proton being there was felt all over, and we just send probes, and there's some potential V of r everywhere. Okay, very good. And it's important, they were there. I mean, by replacing them by a background, we do not put branes anymore at z equal to infinity. Like we don't put a proton anymore once we replace the proton by its effective potential. Okay, very good. So now a few comments. Let's make a few comments about this construction, about the AdS CFT in general, and so on. Okay, the first comment we can make is that we played, this one I made already by the end of last lecture, we played with D3 branes. Okay? We just decided for concreteness to study D3 branes and then did some analysis starting from there. We could, and people did, I mean, we can repeat, we can do the same for other branes, or even more generally, for other heavy objects that exist in string theory. Do the same. Find some geometry, see if there is some decoupling limit, and in this way generate a bunch of very precise dualities. And people did, and therefore by now we have a plethora of examples. But the most well-studied one, is the one I present. So the one I present is the one that is understood the best, where more examples have been done, more checks have been done, and so on. Very good. So this is a trivial comment. Now, a bit less trivial one is the following. Okay, so we got AdS 5 times S5. S5 is some sphere, some compact space. So S5, we have a duality between 4 and 10 dimensions. But what I want to say is that, in fact, it's more, we should think more as 4 versus 5. 4 versus 5 is what is really physically meaningful. The fact that we have a sphere, once you have some compact background, you can always Kaluza-Klein, you can always write the wave functions on that sphere, decompose them into spherical harmonics. You can get rid of the sphere at the expense of putting many fields living in AdS, right? Is it clear? So whenever you have a physical system, which is something times, say, a circle, you can expand your wave function into the modes, periodic modes on the circle, and then you have some theory on the lower dimensional space-time, but now you have an extra quantum number which tells you about the fact that there was a circle there. Yes?
Do the spherical harmonics easily extend to higher dimensions?
Yes, yes. Yeah. So S5, I mean, we can trade S5 by just having many fields in AdS5. Okay, but AdS5 is non-compact, so then we cannot continue this game. Okay, so this guy is compact. Okay, so this is what is called, maybe you have heard this, I'm talking about just Kaluza-Klein reducing. But AdS5 we cannot. So we have a duality between at least a 4D quantum field theory and a theory of 5D quantum gravity. And this nature of this duality, this is why these dualities are often called a realization of the so-called holographic principle. The holographic principle is the principle that quantum gravity should be holographic, that is, it is described as if it were an hologram by just a theory in lower dimensions that lives at the boundary of this gravitational box. So we have a boundary of our box, like our crystal ball, And at this crystal ball, we describe the full action going on in the ball, the 5-dimensional ball. Okay. And let me just tell you some very basic arguments. One of the arguments why people thought that holography should be an important principle of nature. Why it should be that holography should be something built in our description of quantum gravity. So why do we expect holography from a totally different point of view? Okay, so there are many arguments towards holography, but let me give you the most known and simple one. And the simplest argument is telling you that if you have some given region with some volume V and some area A, that the amount of entropy, the maximum entropy that you can have, is not proportional to the volume, as you would expect, but to the area, as you would expect if the theory was holographic, if the number of degrees of freedom were proportional to the area, not the volume. Okay? So if I can argue that this is true, then you would be convinced that gravity should indeed be holographic somehow, because the maximum entropy, the maximum number of degrees of freedom in some volume, is finally just proportional to the area and not to the volume of this volume. Okay? And we can argue this very easily by saying that suppose we could reach an area if S is bigger than S max, continue throwing stuff inside this volume, until we form a black hole. At that point, when we form a black hole, the entropy will be the area of the black hole over 4. So what would happen is that you would start with some entropy, you start throwing stuff inside, so the entropy continues to increase, and suddenly it becomes area over 4, which means it decreases. But that's impossible. At that point, that decreases, so the end, and this is impossible. It violates the second law. Therefore, this hypothesis is ruled. So there ought to be indeed some principle that tells you that the maximal entropy in some region is proportional to its area, that indicates that if there is some description of quantum gravity, the quantum description of quantum gravity should somehow be holographic. And the AdS CFT is a beautiful realization of this idea. It tells you that indeed gravity is holographic. If you want to describe gravity, you can describe it by a very precise quantum theory, which is n equals 4 super young mills in this example, in 4 dimensions. And this is how I describe gravity in 5 dimensions.
I'm not quite clear about the argument.
The argument is that if you have, imagine I have here some crystal ball, and inside the ball, I have some volume, and inside this volume, inside this room, there is more entropy than area over 4. Now start to ask more people to come in until it's so heavy that it forms a black hole. Right? Put more stuff inside till it forms a black hole. When it forms a black hole, the entropy of a black hole is area over 4. I mean, this I'm confident that you have seen. So that would mean that you start with some entropy, you start increasing it, and suddenly, poof, area over 4, it decreases. That's impossible.
So here, the S max is for the general case.
Yes.
Not the back.
No, this is, I'm telling you, this is for general case. Whatever happens here, okay? I have some people inside. Whatever happens inside this region, the maximal entropy that they can have is area over 4, okay? If you have this is someone's room, it's totally not tidy. There's a huge entropy, but still it's smaller than area over 4 for sure. Okay? These are clothes in the floor. Okay. Yes?
But the thing you said there about S5 being representable by many fields in AdS.
Yes.
I think I understand, but I'm a bit confused because I thought we used the decoupling argument yesterday exactly to argue that we can ignore the things outside of AdS, but this seems a different argument for the same purpose.
No. We can ignore things. We can stay with AdS 5 times S5. Now this is a very different argument. There's nothing to do with the decoupling link. So we have some space-time which is 10-dimensional. We zoom close to the brains and we have some 10-dimensional space-time. that time-dimensional space-time, AdS 5 times S5, is decoupled from the flat space region very far away from the brane. Okay? Now we forget about that geometry. Now we always discuss AdS 5 times S5, always. Now in that geometry, you have some AdS and you have some sphere. Now the sphere and AdS actually come with the same radius. Okay? So suppose AdS is roughly the size of this room. Okay, so you have some, okay. At the size of this room, I mean it has the radius of the size of this room. So the space-time changes at distances roughly of the scale of this room. It's non-compact. But you see the distances by which the space-time changes significantly are of the order of the space of this room. If that is the scale you are working with, then your sphere is a sphere of the size of this room. Okay? So of course, it's a huge sphere. It's not like the example I said before, where you have some plane times a very small circle, and you Kaluza climb the circle. So of course, that's why I say that you have to keep many fields. It's not just the first few. Because, I mean, it's not really a very controllable approximation to Kaluza climb a sphere that is as big as the space-time where you are. Right, but you can do it conceptually. But even if you could not, okay, all I'm saying is that you have a higher dimensional, the theory is a lower dimensional theory. And even if you consider here the full 10-dimensional spacetime, you can still ask, what is the boundary of that spacetime? And the boundary of that spacetime is comes from the AdS part, and it is this part here. Okay, very good. So this is one argument that tells us that finally it's quite cool that we found this higher dimension. It is a precise realization of this holographic principle. There is another reason why we should be very happy to find that we do not get a duality between a 4D theory of gravity and the 4D quantum field theory. And the reason is that there is a theorem that tells you that this is impossible. And it's a theorem by Witten and Weinberg, so we better be careful. So there is a theorem by Weinberg and Witten that tell you the following. A quantum field theory, like n equals 4 super Young-Mills, with Poincare invariant stress tensor, forbids particles with J bigger than 1. And with some p mu. It's just some technical assumption. Ignore this last one. So basically what they show is that they show that if you take a particle, say with spin 2 and some momentum k, p mu nu, spin 2 and some other momentum p, this behaves very badly. And therefore they rule the existence of these spin 2 guys. And spin 2 is the graviton. So it tells you that if you have a theory with a Poincare invariant stress tensor, you cannot have particles with spin J bigger than 1. Of course, let me remind you that in gravity, the full T mu nu is equal to 0, so you don't have a problem. Okay? So delta S, delta G mu nu is equal to 0. But there is a big assumption here. And the assumption in this theorem is that the graviton lives in the same space-time as the quantum field theory. That is, the assumption that you start, say, from a large N theory, and you start getting some effective description of closed strings that in particular contains the gluon. But why should this gluon that we see the strings propagating, why should a space-time where the strings propagating be the same space-time where we started defining our theory? It doesn't need to be. Right? Doesn't need to be. We get some effective description of strings propagating, but why should they propagate in the same space-time where they start? And indeed, they don't. We have a description of 4-dimensional theory, but the effective strings, they live in another space-time. Okay? So gravitons live in the same space-time, but the point is that they don't. So we evade problems that we would get otherwise. Okay, so it's another argument why this sounds good. Now, here we have AdS, okay? And AdS is a space-time that has this scale invariance. Okay? So now another argument why we would expect to, why another comment about what we just got. Okay? So AdS has scale invariance as an isometry. Okay? And if we have some theory of quantum gravity, where we have some conformal field theory living at the boundary, this better be true. What does it imply? It implies that if this is the boundary, z equal to 0. Suppose you consider some process in the bulk which is related to, you put some two sources, say two operators, close to each other, and consider, say, some minimal geodesic or some minimal string, doesn't matter, close to each other. Okay? So this is a short distance, so this is some UV process in the CFT. Now you could imagine considering another process where you put the two probes very far away in x, at z equal to 0, and you would have some IR process in the CFT. Now, in a conformal field theory, so what happens is, what we see is that this direction z, here, this direction z is related to the distances. Okay, so you can think of this as some RG direction. That, you see, as you probe processes that are very ultraviolet processes, you almost don't go inside AdS. If you start probing processes that are very separated apart, you will feel the region well inside AdS. Of course, in a CFT, this RG is trivial. So you can think of RG as telling you how correlation functions at different distances in a given quantum field theory change. Now, in a conformal field theory, correlation functions here, or here, or here, they are all the same. You just dress out some trivial space dependence, and then they are invariant under dilatation. So this invariance is mapped into the statement that if you have, say, some string process, there is an isometry that maps this process to this process that maps string solutions to other string solutions. Okay? Is it clear? So if you, okay. So the fact that you have an isometry in AdS that allows you to relate some string path integral or some string solution to a bigger one just by using an isometry is something that you would need if you would want to reproduce in the boundary some theory that also has some trivial transformations, as you consider some process and a much bigger process and a yet bigger process and so on. They should all be related in a trivial way. So if this is the process for a string that is close by, this one should be related by this in a very trivial way. So that tells you that if you have some foliation of AdS, if you have some foliation of Minkowski in the form dx mu, and you want to somehow foliate it by this kind of picture based on the RG, you are led uniquely, as we also argued the other day, to adding an extra coordinate z in this way, and this is nothing but AdS. And this intuition also tells you that if, on the other hand, we would like to have a duality between a theory that is not a conformal field theory and the theory of quantum gravity, then we can imagine what should happen. What should happen is that as you go inside Z, you can have some non-trivial Z dependence, such that as you consider probes that are more and more separated, they do not behave in the same way. They behave in a different way. And in this way, you can encode some non-trivial behavior with scales by considering some spacetime which is just not AdS. Okay? So non-trivial Z foliation, Z dependence, would be related to dualities between non-AdS spacetimes and non-CFT theories. And there are such examples as well. And this picture is also very tightly related to things that maybe Gifford is telling you at this moment about the fact that you often think of this. You can also do some renormalization of your underlying theory, and you can draw some cute pictures where you generate some effective direction, which I see one here, where you generate some effective direction that is exactly this z direction, right? So apparently you have seen this today or something like this, right? So you have some boundary, and then as you go inside to probe stuff that is further and further apart, right? So if you probe a correlator function here and here, you have to sum over all these tensors here. It becomes further and further apart as you are going inside the bulk. Okay. Very good. And then this leads to yet another kind of more or less derivation of AdS CFT. Because you could ask yourself, okay, suppose I know exactly what it means to put probes at the boundary of AdS. Okay? Suppose I did, and this is a big suppose, because in practice it's kind of tricky to find out what exactly are the vertex operators that you should put in string theory. But suppose that was a problem that was well settled and you knew how to insert strings at the boundary of this spacetime. Okay, purely a process within string theory. Forget about CFT. Then you could ask yourself, okay, let me consider my AdS spacetime. So this is the z direction. So this is AdS. And let me insert some strings here. Or it can be in the regime where the tension is very big, and then this would be just particles. This fat solution should look more like just some three geodesics uniting. Let me consider this process. So you integrate over all surfaces and so on. And let's use this to define some correlation function, O x1, tac, 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 O x3, in some mysterious CFT. So we define this, quantum field, mysterious theory. Let's just call it theory. So we have a spacetime, it has a boundary. And we say that this procedure of doing this quantitation in quantum gravity defines something that depends on points on the boundary. Let me, in this way, define a mystery theory that lives at the boundary. Okay, it's a definition. Is it okay? Yeah? But now you ask, okay, so what symmetries does this guy have that will imply symmetries for the boundary theory? So this is a superstring theory. Okay, that has this SO1, comma D plus 1 times SO, okay, let's write SO1, comma 5 times SO6 symmetry. Okay, so this is from the isometries of AdS, these are rotations of the sphere. Plus, it has fermions and it has supersymmetry. And because we have these isometries, what they will imply is that the boundary theory will get these isometries, they will become symmetries as you approach the boundary. And this will imply that the dual CFT, whatever this theory is, it will have some symmetries, it will inherit symmetries from the bulk. And because this string in AdS 5 times S5 has a lot of symmetry, you can show that the symmetry that it inherits is is the same symmetry as n equals 4 super Young-Mills. Okay, it has super conformal symmetry. It has the full symmetries that n equals 4 super Young-Mills should have. Okay? But now n equals 4 super Young-Mills is kind of a special theory. It's called also, some people also call it maximally supersymmetric theory. If you start writing a Lagrangian, if you assume that n equals 4, that the theory you get has a Lagrangian description, again a big assumption, some theories don't. There's only one Lagrangian which has n equals 4 supersymmetry, which is the Lagrangian of n equals 4. Then you would prove the duality. Okay? So if this is the same as n equals 4, okay, so n equals 4 is maximally supersymmetric. So its Lagrangian is fixed by supersymmetry, if it has a Lagrangian.
So the just only assuming that, so simply assuming that the boundary is described by Lagrangian is enough to indicate AdS CFT then, or is it?
No, I mean this is unwavering for many reasons. It's unwavering because I don't know, strictly speaking, no one knows precisely how to insert these strings at points in the boundary. I mean, it's not something that you could right now put in a computer that is so well defined that you could put in a computer. You know what it means for some simple operators, some simple string insertions, and for those you can indeed check that all this works. But it's kind of a hand-wavy argument. For it. Okay, very good. So I think this concludes what I can tell you about why this is a natural duality. I think it's now extra evidence for the duality will come from playing with both sides of the duality and seeing that we get similar and sometimes the same result. And similar, I will explain what I mean by similar. So just some general comments about how people use this duality, about some general blah blah about how people use this duality. Okay. So AdS CFT, it is very natural. There are at least 3 very important branches of thought that you can follow at this moment. So one approach is to think of AdS CFT as a definition of the gauge theory. And by this AdS CFT, I mean in the broad context. Okay, not just for this example on n equals 4, but more broadly. AdS CFT general dualities between AdS and CFTs. So you can use them in the following way. You can say that you have some theory in AdS, so some theory in AdS. It can be something rigorous. It can be some string theory that really we know how to define. You know it's a conformal field theory, some AdS 5 times S5. Or sometimes people use it more from a phenomenological point of view. You put some theory in AdS with a bunch of fields, and you consider only the gravity approximation, and you put some theory in AdS, and postulate that it describes, by following the dictionary carefully, that it somehow defines some boundary theory. Okay? By saying that it defines some boundary theory. And then explores what this definition gives. So this has applications for study of so-called applied AdS CFT. People that use this AdS condensed matter, AdS Rick physics to study quark gluon plasma. This is a bit more solid than the first one. Phenomenological approaches. Let me emphasize, sometimes, for example, when you study the quark gluon plasma of n equals 4 super young meals, this can be made rigorous. If it's the quark gluon plasma of QCD, you have to somehow put some phenomenological terms by hand. But sometimes it is quite phenomenological. So what you do is, for example, you want to study correlation functions of some theory, and you know more or less how they behave with distance. So by hand, you put in some space that is not exactly AdS, but something that will give you what you want to get. It's not something very honest if you want. And you fine-tune your space to get what you want for your 2-point function. But then you do something honest. You go and ask, okay, this I put by hand, but now let me compute other stuff, say 3-point function, specific heat, and so on, and see what do I get. You see? So you put in by hand some stuff. So people say, who do AdS condense matter? They typically put in, they have AdS, they add some gauge fields, they add some fields, and so on. They put some stuff by hand that they don't really have a very strong justification, except that they know this is what they must put to get to describe some physics that are relevant for the theory at the boundary. And then what you try to do is you put a little bit, but you try to take more out than what you put. Okay? So this is a kind of a phenomenological approach. Okay. You can also approach this, you can also think of this kind of dualities more in the spirit of a definition of quantum gravity. Okay. This is maybe a bit less popular, saying that, okay, I have some CFT in the boundary, and I use it to define whatever I mean by quantum gravity. Now, this, I like it very much. It's kind of a very powerful point of view. It has immediate consequences. Say, as soon as you say that n equals 4 super young meals should be equivalent to full quantum gravity in a box, you are immediately telling, for example, that there can be no information paradox. You are immediately telling that because the evolution on the boundary is manifestly unitary, it is just a unitary quantum field theory, there is no place for breakdowns of unitarity and for information loss and so on. Whatever is the computation you have to do on your CFT that describes putting some probes on at some point that form a black hole inside the box and then the black hole evaporates, whatever it is, it will be complicated for sure. But whatever it is, it will be described as some unitary process because the CFT is some unitary theory. Of course, I mean, a very important, it is worth emphasizing that a very good dictionary is crucial, of course. And it's very important to have one. Another point of view that probably is the one that we will mostly follow in the last week is the point of view of a tool in the following sense. A quantum field theory, how should I call it? Helper, I don't know, guide. And also a string guide. For solving these theories. That is, AdS-CFT sometimes throws some provocations at you. What I mean by this is, suppose, according to AdS-CFT, you predict, by studying both sides of the duality, that some quantity should behave in a given way in a regime that previously you did not know how to compute. Because, as we said, this duality maps the easy regime of one theory to the hard regime of the other, and vice versa. So often, you can very easily generate predictions that are very hard to check on the other side. Okay? But if they are very precise predictions, like the scaling dimension of this operator when lambda is very large should be lambda to the 1/4 times 2. And you see some very, very precise analytic prediction that you have from the gravity side, and then you say, okay, now in Young Mills I have no hopes of getting this. And then you say, no, this cannot be. I mean, if I have analytic results, I must develop analytic techniques to nail them down. You see, it converts problems that you ask in either theory, instead of being these kind of hard problems that we often don't like, which is find what this result is, it makes the problem show that this is true. Okay? It converts all your exercises into prove that the dimension of this operator behaves as in this way. So it tells you what the result should be. Then you try to honestly rederive it. So it's extremely powerful as a way of giving you data, giving you information to play with that you can use to develop new analytic tools to solve quantum field theories and to quantize string theories. Okay? Okay. So So it's a guide for solving these theories by solving these theories independently. And a side product of this, I don't think it's the most interesting byproduct, but the byproduct of this approach is, of course, that at the end of the day you will prove AdS CFT. Because if you develop it so much that you can independently compute from both sides at the end of the day in the regimes that previously were known as hard, but now they are humanly accessible, at the end of the day you show that the theories are the same. It's an outcome, a natural outcome of this third point of view. So of course this point of view is very much related. Remember that AdS CFT, let me emphasize it again, is a weak-strong duality. So we have that what is easy from the gauge theory, which is very small coupling, perturbative gauge theory. Okay, so this is perturbative gauge theory, becomes dual to highly curved strings, so very quantum and hard. Okay? So when lambda is very small, it means that the radius of my AdS is very small in string length. It's a very curved spacetime, and I have the strings are strongly interacting. Another way of thinking is that you see that action over there. When lambda is large, only classical solutions of the string equations of motion dominate, because it's right. When lambda is large, if lambda is small, you have to sum over all fluctuations, and the tension is not suppressing anything. So it's very quantum strings. And what is very hard on the gauge theory, strong coupling on the gauge theory, which is lambda much bigger than 1, is mapped to classical strings, which is easy. Okay? And sometimes even simpler than classical strings. If not only you have classical strings, but if the tension is even so big that you don't scale the quantum numbers of your string, and you don't scale the quantum numbers of your string accordingly, what you will do is you not only will suppress fluctuations, but you will squeeze the string and it will become a point-like particle. So you get the field theory limit of string theory, which is supergravity. The field theory limit of that. So you can get classical strings, or even simpler, or even just supergravity if you really pump up the coupling even more. So then you really get the simplest possible thing, of course, by today's standards, like doing computations in supergravity, being dual to very, very hard regime of gauge theories. Okay. So let me see. Do I want to go into this? It will probably take me. Okay, so what do we need to know now? Well, what are the natural questions that we now want to address, that we want to know the answer to? So, so what do we need? We need to go on now. We need to know more about n equals 4 super Yang-Mills. You are probably looking forward to see at least what the Lagrangian looks like. We need to know more about strings in AdS 5 times S5. What's the action and so on. We need to know the dictionary. And we need convincing checks. And this is what we'll try to do next week. Okay. But I still have some time, so I think I'll start the third point of establishing a bit the dictionary, or at least reminding you a bit about some facts about the geometry of AdS. Okay? Okay, very good. So let's discuss a bit these 2 points here. Namely, let's discuss a bit more on the geometry of this space-time called AdS, and it will automatically tell us more about the dictionary and the relation between energies in our dimensions in the field theory and properties of strings in this space. Okay. So first of all, is everyone familiar with these pictures? I think these pictures were in your second tutorial. So did everyone play with this kind of pictures? Is this familiar to everyone now? Yes? So can I assume that you understood the geometry behind this? Okay, so I'll just summarize it very briefly. And maybe so let me just, basically I'll be summarizing what you understood already. So as we have seen, AdS has several incarnations. So you can think of AdS as a given space-time dependent in different ways. So one way of thinking about AdS is as a pseudosphere, as an hyperboloid, where you just have an hyperboloid, y minus 1 square plus y0 square minus y1 square minus y2 square minus y3 square minus y4 square equals to 1. So you embed your your hyperboloid in a space of one higher dimension, and you have this picture of an hyperboloid, and this is one depiction of AdS. Okay? So let me maybe first comment on how do we see that in this language that the boundary of AdS is flat space. This is an hyperboloid. The boundary of the hyperboloid is this infinity here, right? So how do we see that this is flat space? Well, it's actually quite neat. Let's imagine a light cone that goes through the origin. I didn't draw it properly. What a pity. Okay. So if you draw a light cone, I should always draw the light cone first and then the hyperboloid, of course. What happens is that you can see that the hyperboloid asymptotes to the light cone. Oh, this is a disaster. Okay. So you can think that if you have some light cone, so this is a light cone in R2, 4 in 6 dimensions. Then you have your hyperboloid, which asymptotes to this light cone. Okay? By the way, this thing 1 here, this 1, means that here in the middle, this circle here, is 1. Okay? But normally this would be L. Okay? So I'm choosing radius to be 1 to draw this picture. Okay? So the radius of AdS is telling you how small that circle is on this hyperboloid there. Okay? Or L square. Okay, very good. So we see that the boundary of AdS, the point which is approached, is equivalent to the space of light rays in R2, 4. Right? A light ray asymptotes to a point in the boundary of AdS. So for each light ray, say here is a light ray, for example. For each light ray, okay, here is a ray, x, where x squared equal to 0. This is in 1-to-1 corresponds to points in the boundary of AdS. Right? But now you remember that we saw that when you have a conformal field theory, and in general, a nice way of thinking about flat space is as a set of light rays in 2 higher dimensions. This was the subject of one of the tutorials. So indeed, light rays in R2, 2 are nothing but flat space. Okay. And I remind you that Lorentz transformations in this R2, 4, they preserve this hyperboloid, and they are equivalent to conformal transformations in the boundary. Okay? So this is a neat way of understanding that indeed the hyperboloid as the boundary contains Minkowski space. Very good. Then we saw that if you have this description in terms of an hyperboloid, you can change coordinates and go to the description in terms of the so-called Poincare coordinates. Okay, where this is z. So these are called Poincare coordinates. This is just by choosing some parameterization that solves these constraints and then plugging it into the flat metric in R2, 4. And there was another incarnation of this spacetime, which was just what is called AdS in global coordinates, which is minus cos square of rho dt square plus d rho square plus sinh square of rho d omega of S5, where this one we represent as a cylinder. Okay? And these lines here, this line represents a 5 sphere. This is a representation of, no, probably not a, sorry, not a 5 sphere. 3 sphere. This is a representation of AdS5 again. Okay, so here is Minkowski 4-dimensional, and here is this sphere. Okay, very good. And then we see that actually, what's the boundary of this spacetime? Well, the boundary of this spacetime is nothing but Minkowski. Again, this is the boundary, this boundary of AdS. Okay? But here, the boundary of this spacetime, here, from this point of view, the boundary of AdS, let me add the subscript global to indicate that this is in global coordinates, is not Minkowski, but it is time, so it is RT time times a 3 sphere. Okay? So, okay, this looks a bit funny. How come suddenly we get a different boundary? The boundary is just time times this 3 sphere. Let's understand it in a minute. But let me just remind you of some of the physics of this block. This, if I understand correctly, not everyone finished, but I think you have the solution online. If you consider trajectory of geodesics in this spacetime, they behave as a gravitational box. So this is something quite nice in this spacetime, that this spacetime behaves as a gravitational box. So there are different advantages of this spacetime. So I mean, for example, one very nice advantage of this spacetime is exactly this. This is something we like very much. I mean, to have some box where we can do our experiments is something cool. This is something good for sure. These coordinates, we also like them very much. These ones, for example, are the ones that arise from this brainy derivation. Right? I mean, these were the coordinates we were led most naturally when we were considering this picture of brains and so on. This was what was naturally coming about. And this is nice. I mean, this is a pseudosphere, so this is a very nice geometry. From a geometry point of view, this is kind of a nice object here. Okay, very good. So how does it happen? Well, let's now discuss a little bit these boundaries of this AdS. So remember that if this is your geometry, here you have this time. Okay? This here is what would be time. So the time t under this change of coordinate is this circle here. This is what this time is in global coordinate, this time here. Now this time here, of course, goes from minus infinity to plus infinity. But this original one goes from 0 to 2 pi. It just goes around. Right? This is kind of bad. To have a theory of particles in this hyperboloid, you would start having closed time-like curves. So this is not good. So what can you do? Well, you can simply say that I start here. And as I go around, I don't come to the same point. I come to another sheet of this hyperboloid. So you can wrap several sheets of paper here around infinitely many times, like toilet paper. Then you go around and you come to another sheet and you never come back to the same position. But very thin toilet paper, of course. Coinciding toilet paper. So this is what this picture here is of the hyperboloid. So that's more natural physically than this one. This is what's called the universal or the universal covering of the hyperboloid, because you cover it several times. Okay, then the boundary is no longer AdS. Now it becomes many copies. It's not only Minkowski, it's many copies of Minkowski. You go around and you get many copies. Very good. So now, from that point of view, the boundary, it will be many copies of AdS. Here, we have just a single copy. How does this fit? This fits because this space-time does not cover the full hyperboloid. It covers part of the hyperboloid, this part in orange here that you saw in your lecture. And if you try to map it to the cylinder, you also see that it doesn't cover the full cylinder. It covers what's called the Poincaré patch of this cylinder. It covers some wedge of this cylinder here. Okay? So the way to think of these multi-copies of Minkowski as the boundary of the cylinder, the way we can think of these multi-copies as the boundary of the cylinder is actually quite simple. So you can think of it in the following way. You have your cylinder. And if you follow the map between one copy of Minkowski and the boundary of this cylinder, so you know that one copy of Minkowski, the Penrose diagram is just this napkin. Okay? So this is Minkowski. Okay? This is just a Penrose diagram. And this boundary is mapped into this picture by the thing that you take this napkin and wrap it around. So then you have something like this. Let's see if I can draw. And you wrap this napkin around here. Okay, I clearly don't know how to draw very well, but okay. You have some napkin and you wrap it around. Is it okay? But now you can imagine that you can put, so here is one. You can think that here in the cylinder, what we have is many patches glued together. So you can have, so this is one Minkowski, this is Minkowski minus 1, here I will have Minkowski plus 1, and I will have n copies of Minkowski where n belongs to z. I would have a sequence of Minkowski of napkins that I can put around the cylinder, one like this, one like this, one like this, one like this, and so on. And indeed, if you have your field theory, if you have your conformal field theory that lives in Minkowski, it's possible to consider the generalization where correlation functions live in an extended space, which is an infinite copies of Minkowski. So this was actually understood a long time ago, that the CFT can be analytically continued to the full cylinder, the full extension of not just one Minkowski, but the full copies of Minkowski. Okay? There is a remarkable, beautiful paper by Mach and Luscher. They call this n bigger than 0, these copies of Minkowski that are above, they call them spheres of heaven. And the n smaller than 0, they call them circles of hell. So you have this infinite set of circles of hell and spheres of heaven that you can stack. You see, you can imagine if this is the cylinder, here it's much easier to draw. If this is the cylinder, then you are just stacking like this. So this is Minkowski 1. This here, it's going around, it's Minkowski 2. This is Minkowski 3. The next one will be Minkowski 4, and you can have an infinite set of them. Okay? Okay, very good. So this is how things can fit together in the same coherent picture. And then, and therefore, we can have our CFT indeed living in two spaces. We can have our CFT living in Minkowski space, or we can have our CFT, if we want, living in R times SD. Okay? So it's up to us. We can study n equals 4 super young Mills in Minkowski space, or we can study n equals 4 super young Mills in time times a d-dimensional sphere. And then the claim is that n equals 4 super young Mills in Minkowski space is dual to strings in Poincare coordinates, whereas n equals 4 super young Mills in this time times sphere, so n equals 4 super young Mills defined on the boundary of this cylinder, will be dual, of course, to strings in global coordinates. Okay? So I apologize for going over time, but I want 5 more minutes to finish this argument. Okay, very good. Then, these global coordinates, they have some time t. Okay, so now pay attention. This is a simple argument, but if you miss the words, you might miss the argument. So this global time has some time t. Okay, so t is the AdS global time, but it's also equal, let's call it, to the n equals 4 time, or to the brane time. And as you go to the boundary, your metric behaves as e to the 2 rho times the flat metric, the metric on the cylinder, dt squared plus the metric of the cylinder. So the time on your CFT, which is on time times the sphere, is the same as the AdS global time. So then, we conclude the following. We conclude that if you have strings in your cylinder, okay, you have some strings moving in your cylinder, and the energies of the string. Now, when I specify energies, I mean in a curved space-time, I must say that its energy is measured with respect to some time-like Killing vector, so with respect to some time, measured by someone, in other words. So the energies of the string with respect to the AdS global time, T, in other words, energies of strings put in a gravitational box, well, the time is the same, so this is the same as the energies of the CFT, just because the time is the same, in R times S3. Just because the time is the same, the operator of evolution in time is the same. But remember that one of the nice interpretations of our anomalous dimensions, was this was the same as the spectrum of anomalous dimensions, or dimensions. I just call them dimensions. Dimensions of single trace of operators in R4. And therefore, we establish our first dictionary, which is that if you compute the energies of the string, the spectrum of the string in a box, you put strings in a box and compute the spectrum of strings, it's equal to the spectrum, to an important part of the CFT data, which is the spectrum of anomalous dimensions of n equals 4 super Young net. Okay, very good. Okay, we stop here. Thank you.